Okay, so in the first segment, remember we did an introduction to what carbohydrates are.
Yes.
We said that these molecules contain carbon, hydrogen, and oxygens in the ratio 1 to 2 to 1. Then we said that they range from as small as having just three carbons. And these are what we call the trial sugars, isn't it? The dihydroxyacetone and the aldehyde, so the three carbon sugars. And then of importance also, we said that these molecules have carbonyl functional groups. So it's very important to note that they have functional groups, which are the carbonyl groups. So the carbonyl group consists of a carbon double bonded to an oxygen atom. So C double bond to O. And then in addition to the carbonyl functional groups, we find that also carbohydrates have multiple hydroxyl groups. So these hydroxyl groups are the OH groups. The OH groups. Those are also functional groups that we find in carbohydrates. Let me just bring a diagram. Yeah, so we are saying this is the carbonyl group. So carbohydrates contain these the carbonyl group and also several hydroxyl functional groups. So these are the hydroxyl functional groups, the OH functional groups. And then we said that carbohydrates can be grouped as either aldehydes if they contain aldehyde functional group, or as ketoses if they contain the ketone functional group. So for example, in this case of ribose, this is an aldehyde because it has a terminal functional group. This is an aldehyde, terminal carbonyl functional group. And then fructose is an example of a ketose or a ketone or a molecule consisting of a ketone. So now, from our previous class, we did mention examples of reducing sugars. Examples of reducing sugars. Can you remember any? Any examples you can remember?
Yes.
Yes, like
you
which
talked
one?
of fructose.
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 Yes.
Glucose.
Glucose.
Galactose.
Yes. Okay, yes. So those are some of the examples.
Sucrose.
Which one?
Sucrose.
No, so sucrose is not. It's a non-reducing sugar.
Yes.
So
Okay.
yeah, so we are going to explain further in another session why sucrose is a non-reducing sugar. Why sucrose is yes. So I made a statement that all monosaccharides are actually reducing sugars. So it means the examples that we've given, of course, for example, glucose, galactose, fructose, these are reducing sugars. And I also mentioned that all common disaccharides, so most of the common disaccharides are actually also reducing sugars, except sucrose. So we have disaccharides such as maltose and lactose. So these are actually reducing sugars. However, as we are going to learn further, we're going to see that sucrose is actually a non-reducing sugar. So we're going to learn what makes it a non-reducing sugar. was disaccharides come about through two monomers joining, forming a bond. So there's a way that sucrose forms the bond that makes it to be non-reducing sugar. So fructose, glucose, galactose, and other monosaccharides, the pentose sugars, those are reducing sugars.
Reducing sugars.
Yes, and then I mentioned that aldehyde, those molecules with an aldehyde functional group, those are reducing sugars. They are powerful reducing sugars because that aldehyde functional group, the terminal carbonyl functional group, can easily be oxidized. So if a molecule is oxidized, it means that it reduces a certain other molecule. So in the case of the aldehyde functional group, it is easily oxidized. Therefore, it is a powerful reducing sugar. And then the other question is, why is fructose reducing sugar even though it is a ketose? So remember, fructose as a ketone functional group. And remember, we said that aldehyde functional groups are easily oxidized and hence they are powerful reducing sugars. So why is fructose a reducing sugar even though it has a ketone functional group? What can you
did you say it's because doesn't it have a free aldehydes in its structure?
Okay, so we said fructose. When we look at fructose, even though it is a ketone or it is a ketose, it is able to isomerize into an aldose sugar. So it can be able to change. It can be converted. It can be able to convert into an aldose sugar. So it can convert to glucose. And remember, the aldehyde functional group is a powerful reducing group. So when the fructose converts or isomerizes or changes into an aldose sugar or glucose in this case, then it means that fructose acts as a reducing sugar. So generally fructose is a weak reducing sugar because it's a ketone, but it becomes a reducing sugar because it can isomerize. Is that clear?
All right. Yes, it is.
Okay. Okay, so the next question is, which carbon has a polar bond in dihydroxyacetone? So remember dihydroxyacetone?
Yes, sir.
What kind of sugar is it? How many carbon atoms does it have? Remember glyceraldehyde?
Yes, I do.
Yes. So it's dihydroxyacetone is in the same class as glyceraldehyde. So these are three carbon monosaccharides. They are three carbon, so they are triose sugars. So of the two, which one is dihydroxyacetone? Which one? The one on the left or on the right?
It has good.
Okay, speak up. You can speak.
The one on the left. I don't know how your position. The one on the left.
Okay, which one? Oh, which one with the carbonyl group at 1 or the carbonyl group at 2? Is it this one?
Group at 1.
This one or this one?
Yes.
Which one?
The one with the carbon group at 1.
So this one is a glyceraldehyde. This is glyceraldehyde. Yes, this is glyceraldehyde. because aldehyde has an aldehyde functional group. And an aldehyde carbonyl functional group is at position number 1. So this is glyceraldehyde.
Okay.
So the one on the left is glyceraldehyde. The one on the right is dihydroxyacetone. So dihydroxyacetone has a ketone functional group at position number 2. So this is the dihydroxyacetone. This is glyceraldehyde. So which carbon has a polar bond in dihydroxyacetone? Okay. So carbon, it's either carbon 1, carbon 2, or carbon 3. So the answer to this question is actually carbon 2. Carbon 2 has a polar bond in dihydroxyacetone. So this is because of the electronegativity of the oxygen atom. The electronegativity of the oxygen atom. The high electronegativity of the oxygen atom. So carbon 2 of dihydroxyacetone has a polar bond in dihydroxyacetone. So it's carbon 2. Is that clear?
Yes, it is.
Okay, thank you. Which of the two below has an alpha or is an alpha anomer, and which one is a beta anomer? So which one is alpha and which one is beta? You remember we looked at alpha and beta, right?
Yes, sir.
So from these two, which one is alpha?
The first one.
The first one is
it's an alpha.
Why?
Because the hydroxyl group is below the
plane.
What do you call it again?
Below the plane.
Yes.
Which hydroxyl group? Remember, there are a lot of hydroxyl groups. There's this one, there's this one, there's this one, there's this one, there's that one, there's that one. Which hydroxyl group? Is it this one? Is it this one?
No.
This one?
No.
This one?
No.
This one? Huh? Which one? This one or this one?
That same one, yes.
This one?
Yes.
Yes, so because of the hydroxyl group at carbon number 1, this makes this one to be alpha, because the hydroxyl group at carbon number 1 is below the plane. So you can just see the OH is just down there.
The plane.
Yes, so this one, then this one will be beta, isn't it? Because the hydroxyl group is above the plane. It's above the plane. So this one is
the plane.
Yes, so this one is beta. So we are determining beta alpha, right? Okay.
Yes, sir.
Okay, now what is the relationship of glucose to fructose and also to galactose? What's the relationship to glucose to fructose and galactose? So remember I said that conventionally we start counting at the carbonyl, the carbonyl group or nearest the carbonyl group. So we have carbon number 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So this is glucose. And then look at the highlighted parts, because we are trying to differentiate or to find the relationship that exists between glucose, fructose, and galactose. So glucose is an aldase, right? There's an aldehyde functional group. Galactose also has an aldehyde functional group. Fructose has a ketone functional group, the ketone carbonyl group, right?
Yes.
So you've noted the structures, isn't it? So we need to find the relationship between glucose to fructose and glucose to galactose. And also look at the difference at position number 4 between glucose and galactose. Look at the position of the hydroxyl group. The position of the hydroxyl group.
Okay.
Yeah, so what this means is that glucose, or rather fructose, is a structural isomer. Fructose is a structural isomer to glucose. Remember, fructose is a ketose, it has a ketone functional group, while glucose is an aldase or has an aldehyde functional group. So it makes fructose to be a structural isomer to glucose. And then galactose is a stereoisomer to glucose. So when you look at galactose, when you look at the structure, remember carbon 1, just the same, right? Carbon 2, because they are all aldases, they all contain the aldehyde functional group. Carbon 2,
Yes.
same. Carbon 3, same. Carbon 5, same. Carbon 6, the same. But however, they are going to differ on carbon 4.
Oh, that's,
So when,
yes.
so when you look at that structure, we find that this galactose becomes a stereoisomer of glucose because the hydroxyl group in glucose at carbon 4, the hydroxyl group in glucose at carbon 4. I tried to show a ring structure towards the end of the session. The hydroxyl group at carbon 4 in glucose is actually below the plane. I'm going to find that the hydroxyl group in glucose at carbon number 4, remember carbon number 4, it is below the plane in glucose. And then in galactose, it is above the plane. So I'm going to show a diagram of these two, showing to prove, or rather to confirm, that the hydroxyl group will be below the plane in glucose and above the plane in galactose. So glucose or galactose is a stereoisomer to glucose, while fructose is a structural isomer to glucose.
Okay.
The next question is, so this is the all glucose molecules. The next question, in the next question, we are going to deal with the designation of D-glucose and L-glucose. However, the question now is, how many asymmetric carbons are there in glucose? So asymmetric carbons are carbons that are joined to 4 different groups or atoms. So these are carbons that are joined to 4 different carbons or four different atoms or groups of atoms. So they must be different. So how many does glucose contain? How many chiral or asymmetric carbons does glucose have? How many carbons are connected to 4 different groups or atoms? So remember, this is carbon 1, right?
Yes.
This is carbon 2, 3, 4, 5, and carbon 6. Okay. So is carbon 1 asymmetric? Is it connected to 4 different atoms or groups of atoms? So remember, carbon 1 is connected.
Come again, sir.
I was saying an asymmetric carbon or a chiral carbon is bonded to 4 different atoms or groups of atoms. So I was asking, is carbon 1 a chiral carbon? Is it asymmetric? Is it connected or joined to 4 different carbon, 4 different atoms or groups of atoms? Carbon 1. So carbon 1 is not.
No, it isn't.
It's not asymmetric, isn't it?
No.
Because it is joined to oxygen, hydrogen, and carbon 2 here. So remember, it's forming that bond and that bond. So this one is not a chiral carbon or an asymmetric carbon. How about carbon 2? Is it asymmetric?
Yes, it is.
It is, right? Because it is it's joined to the hydrogen atom here and the hydroxyl group here, and the carbonyl group, the COH group here, and the entire structure of or the rest of the structure, this structure. So it's connected to this carbon here, which is connected to this whole structure. So carbon 2 is also asymmetric or chiral carbon. Carbon 3 as well is also asymmetric because it is connected to hydroxyl, the hydrogen atom, this entire group, and also this entire group. So it makes carbon 2 to be asymmetric or chiral. This is carbon 3 rather. So carbon 2 and carbon 3. Then carbon 4 is also asymmetric as well. So it has hydrogen, hydroxyl group, this entire group, and also this entire group. Carbon 5 is also asymmetric because it is connected to hydrogen, the hydroxyl group, the entire group, this group, and also this group. However, when you look at carbon 6 is not asymmetric. It is not a chiral center. Why? Why do you think it's not asymmetric?
Because it's only connected to hydrogen and
Okay. Yes, it's connected to hydrogen. Guys, let's participate. Let's participate. What do you think? Why is carbon 6 not asymmetric?
Is it because it's connected to the hydrogen?
Sorry, just speak up. I can hardly get you.
Is it because it's connected to the hydrogen and the hydroxyl group as well?
Okay. So it is not asymmetric because it is not connected or joined to 4 different atoms or groups of atoms. Remember, carbon 6 will be connected to 2 hydrogens, isn't it? So these 2 hydrogens disqualifies carbon 6 to be asymmetric because it means that it will be connected, it won't be connected to 4 different groups or 4 different atoms. It will be connected to 3 because you have hydrogen, 2 hydrogens, that's simply hydrogen. Then you have the OH group and the entire of this structure. So you just be connected to 3 different groups. So it is not asymmetric. So how many asymmetric carbons are there in glucose? 4. So it has 4 asymmetric or chiral carbons. Is that clear?
Yes.
Okay, great. So this is just an illustration of what I was explaining. So the asymmetric carbon has 4 groups attached to it, which are different. They have to be different. 4 and have to be different. Okay. The D and L configuration. So look at this structure. So mannose is a hexose sugar. It has 6 carbons. So is galactose. So look at this structure now. Is galactose galactose in this picture? And is mannose D or L? Is galactose D or L? And is mannose D or L? What are your thoughts? Any thoughts? Okay, so this is both structures are actually D. They have the configuration D. So look at D simply stands for, in full, is dextrorotatory. Dextrorotatory. So these molecules are able to rotate the plane of light to the right. The level rotatory rotate the plane of light to the left. And it's from levo and dextro. Levo, dextro. So now how do you know that? How do I know, or how would you know that, okay, this galactose is D-galactose, this is D-mannose. So remember we talked about chiral centers. We talked about asymmetric carbons in our previous question. So is galactose a D sugar or an L sugar? So it's a D sugar, and the mannose is also a D sugar. Okay, so this is how you are going to determine. So by conversion, this means that it was decided that D glyceraldehyde is a reference molecule for the designation of either a dextro or levo rotatory, whether a sugar is a D sugar or an L sugar. So you look at we look at this carbon, the position of the hydroxyl group at the carbon 2 of D glyceraldehyde. So this is the reference molecule. By conversion, this is the one which was chosen. So it means that if the OH here is on the right, it means that this is D glyceraldehyde. If this OH is on the left, then the molecule would have been L glyceraldehyde. So using this conventional molecule, using this molecule as a conversion for the designation of other monosaccharides, we are able to determine whether a sugar is D or L. So remember I talked about the chiral or asymmetric carbons. So for example, glucose, this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5. And glucose has 4 chiral carbons or 4 asymmetric carbons. So we look at the position at the bottom, the OH, the position of the OH at the bottom, the most bottom chiral carbon, the most bottom chiral carbon. So in the case of glucose, the most bottom is carbon number 5. So you look at the position of the OH functional group. So the OH is on the right, then this is D-glucose. This is D-glucose. When you look at this structure, you go to carbon number 5, the last or the most bottom chiral or asymmetric center or chiral carbon. You look at the position of the OH. If the OH is on the left, then this is L-glucose. So D-glucose is has OH at carbon 5 on the right. L-glucose, the OH is on the left. Then,
what does the L stand for?
Levo rotatory, rotating, like rotating. Remember I said that these rotate light to the left, levo. So it's simply, it's not an English word per se. It's not derived from English. The levo and the dextro. So you're going to find in nature, like I mentioned, glucose is actually found as D-glucose. The L-glucose is synthetical, or synthetic, it's manufactured. So in nature, we're going to find glucose. No sometimes we are going to find names such as dextrose. So in here, dextrose, it means this is glucose. For example, in the hospital, sometimes patients are given what is called dextrose. So it simply means that's glucose. D-glucose, so dextrose, do D-glucose. So this is the same situation for a ribose sugar. This is a 5 carbon sugar, a pentose sugar. So it has 1, 2, 3, 4, 5. So chiral carbons, chiral centers or asymmetric carbons, it will be carbon number. Which carbons are asymmetric in this structure? Guys?
Three carbons. 3.
Yeah, so carbon 2, 3, and carbon
2, 3, carbon
4, isn't it?
Yes.
This is not
Yes.
asymmetric. This is not asymmetric. Then how many chiral carbons are there in fructose?
There's 3 as well.
3, right? Is this carbon
Yes.
chiral? Is this carbon asymmetric? Guys, is this carbon asymmetric? It isn't it? Because it has to be connected to 2 hydrogens. So these 2 hydrogens are the same atoms, more like it's the same element, isn't it? A chiral carbon or an asymmetric carbon should have 4 different ones. Then this one is not a chiral carbon, it's not connected to 4 different atoms or groups of atoms. This one is chiral, isn't it? To be connected to hydrogen, hydroxyl, and the entire of this structure, together the entire of this structure. This one is also chiral or asymmetric to be connected to this structure, the OH, the H, and the entire of this structure. Carbon 5 is also asymmetric because it will be connected to this structure, the hydrogen, the hydroxyl, and this group. So this is D-fructose because the furthest or the downmost, bottommost chiral carbon there, the OH is on the right. So this is D-fructose. Is it clear on how you designate whether how you know that this sugar is D sugar or L sugar? Are you able to identify if you are given a question?
Yes.
Yes, sir.
Okay, great. So we shouldn't fail such a question. Okay, so this was the last one. This was the last question on the monosaccharide. So let me try to just find to explain, to give an example of what I meant by the ring sugars, the difference between galactose and glucose. Let me find the structure. Are you able to see my screen?
Yes, sir.
Okay, so we said that galactose is a stereoisomer of glucose because when you look at the OH group at carbon number 4, so carbon 4, look at carbon 4, the OH group in glucose is below the plane. Remember, whether it's alpha glucose, okay, so whether it's alpha glucose, this is alpha glucose because the OH is at carbon number 1 is below the plane. And this is beta glucose because the OH at carbon number 1 is above the plane. So whether it's beta glucose or alpha glucose, at position 4, the OH at position 4 in glucose will be below the plane. So this is what we mean, it is below the plane. So galactose is a stereoisomer of glucose because the OH on carbon 4 of glucose is below the plane, carbon 4. However, when you go to galactose, the OH at carbon 4 is above the plane. So not that one. Carbon 4 below the plane in glucose. Let's look at galactose. So this is galactose. So remember, carbon 1 and carbon 5 will be involved in the reaction to form the galactopyranose ring. So remember, carbon 4 in glucose, it is below the ring, the OH, but in galactose, it is above the ring. It is above the plane. It's above the plane, above the plane. Whether it's beta galactose or alpha galactose. When we look at position 4, so 1, 2, 3, 4, carbon 4, the OH is above the ring in galactose, while in glucose it is below the ring. So hence glucose, or rather galactose, is a stereoisomer of glucose. Glucose and galactose are stereoisomers. Have I made sense on this point? I just wanted to clarify it from the area statement.
Yes.
Okay, great. Do we have any question? Any question, guys, or it's clear? I hope it's been helpful.
Yes, sir.
Okay, if it is clear, then that's great to know. And we may end the session. See you next time.
Right. Thank you very much.
Thank you,
Thank you,
sir.
sir.
You're welcome.